Dear participants, my name is Murude Celikag. I'm a senior lecturer at Eastern Mediterranean University in Civil Engineering Department. I'm going to present research findings on failure mechanism of symmetric and asymmetric cellular steel beams. This is part of an ongoing wider research on steel cellular beams carried out in our department with my PhD student, Mohammad, Sehwail, and myself. Since their introduction in structures, cellular steel beams have been popular, particularly for long spans. I can give the following as examples to the advantages they provide. They improve the mechanical properties of beams and allow the passage of service ducts, which decreases the overall height of the building. For those who may not be familiar with this built-up beam, cellular beams are achieved by cutting a hot-rolled I-section in a certain pattern along the beam web, as shown in Figure 1, and then shifting and welding the cut parts together to form circular holes at beam mid-depth. And hence we can call this symmetric cellular beams. While carrying out the wider research, we as authors question the possible consequences of having these circular holes being offset from the mid-depth of the cellular beam, in which case the beams can be called asymmetric cellular beams. This may happen as a result of errors during fabrication or welding. On the other hand, if there are benefits in having an asymmetric beam, then it can be achieved intentionally too, as we did. Hence, the authors decided to carry out a numerical study on the effect of holes shifting on the overall load carrying capacity and on the failure modes of non-composite cellular beams with symmetric and asymmetric sections. Both symmetric and asymmetric cellular beams were made from the same root beam. For this reason, two root beam sections, HEA 340 and IP 330, tested and the results reported in literature were validated by using Abacus software to carry out this numerical study. Mid-span concentrated loads were used and beam ends were restrained with fork condition. Table 1 shows the geometrical details of the 5 IP root beam sections ranging from 200 to 360 that were used for this numerical study. All had the same yield stress, which was 345 megapascals. The three stages of the work done include symmetric cellular beams, where the perforation center line lie exactly at mid-depth of the beams, and the other two asymmetric cellular beams, where the perforation center line lie either above or below the mid-depth of the beams by 10, 20, and 30%. This is percent of the solid part for the beam sections considered in this study. And this 10 to 30% corresponds to around 0.6 to 1.7 centimeter. As an example, we can look at table 2, example of results. First of all, we should note that the asymmetric cellular beams with perforations shifted above the mid-depth show no improvement in the load carrying capacity and the vertical deflections. Hence, the results were not reported. On the other hand, all beams were designed to fail under shear, achieving wear and deal mechanism or web post buckling. So if you look at table 2, it shows the ultimate load, the vertical corresponding deflection, and the corresponding failure mode of symmetric sections and asymmetric sections with perforations shifted 10% down for all sections. Regarding ultimate load achieved, when symmetric and asymmetric sections are compared, a line can be drawn between the first three and the last two sections, where an asymmetric section achieved higher loads as for the vertical deflection and failure mode IP 200 and 240. Asymmetric sections had higher deflection and all sections had the expected Verendeel failure mode. Whilst for IP 240 to 360, asymmetric sections had lower vertical deflection than symmetric ones and the failure mode varies. For example, they achieved either Verendeel plus web post buckling, and for the two deeper sections, there was Verendeel plus Verendeel achieved plus top being web post buckling, and Verendeel at the bottom plus web post buckling. And the deepest section had web post buckling. Considering these, we can also look at another summary of the results of these particular sections that were considered. For parent sections, which we call them shallower sections, there were improvements in the load carrying capacity. The failure mechanism was not affected. IP 240 failed under a combination of Verendeel mechanism and web post buckling, where the strain hardening was degraded compared to the counterpart symmetric section. And when we look at the deeper sections like IP 300 and 360, overall load carrying capacity decreased, and the plastic hinges were observed at the bottom part of the holes, unlike the symmetrical section where the plastic hinges were observed at the top part of the holes. And the authors name this particular phenomena as weak web post buckling and strong web post buckling. In weak web post buckling, the plastic hinges were dominated at the bottom, where for the strong web post buckling, the plastic hinges were at the top. This is for an asymmetric, and for a symmetric section shown in figure 3 as A and B. This slide gives us all the 5 sections with symmetric case and asymmetric case, where the holes were shifted down only. As we said, the ones that were shifted up, it's not reported here. Mid-depth showed no improvement in the load carrying capacity and vertical deflections, hence results were not reported here. Asymmetric cellular beams with perforations shifted below the mid-depth and made from a shallow parent section, which is IP 200, 220, and 240, showed an improvement in the overall load carrying capacity and vertical deflections, where when we consider the deeper parent sections, IP 300 and 360, these show no improvements when compared to the shallower ones tested in this study. Besides, the analysis showed that the shifting of holes affect the failure mechanism through the location of plastic hinges, named by authors as weak web post buckling, where the plastic hinges are at the bottom side of the holes, and this is auto-plane web post buckling, and a strong web post buckling due to plastic hinges at the top side of the holes, which is in the case of in-plane web post buckling. So for the validity of these results to more general cases, the study should be extended by varying the main parameters of the cellular beams, such as the diameter and spacing of the holes, parent sections, depth and slenderness ratios. Thank you very much for patiently listening to me.